Hello and welcome to the Video Labs Academy. In this video lecture, I will talk about light and human vision. In order to understand how CCTV works, we really should understand more about light, the basics of it, and the human vision itself and how human eyes work. So light is one of the basic and greatest natural phenomena, vital not only for life on this planet, but also very important for the technical advancements and ingenuity of the human mind in the visual communication areas such as photography, cinematography, television, and certainly closed-circuit television. The main source of light for our planet is, as we all know, our closest star, the sun. But even though it is so basic and we see it all the time around us, light is the single biggest stumbling block of science. Physics, from a very simple and straightforward science at the end of the 19th century, became very complex and mystical. It forced scientists in the beginning of the 20th century to introduce the postulates of quantum physics, the principle of uncertainty of the atom, and much more, all in order to get some theoretical apparatus and explanation that will satisfy a lot of practical experiments which were made then and equally make sense to the human mind. So what was the major problem? The major problem scientists faced at that time was that when researching light, it acts as if it is of a dual nature. Sometimes it behaves as though if it is of a wave nature. Other times it acts as if it is of a particle nature. So typically when we analyze optics, we treat light as if it is of wave nature. Yet when we treat certain effects like photo effect, we then treat light as if it is of a particle nature. Speaking of the photo effect, this is a very important effect that we will talk about later a bit more, but in essence it is the basis of how we create images from light. Basically, photons are creating electrons in imaging sensors, and those images are proportional to the light that we see in front of the camera. So in other words, the photo effect converts the visual image in front of the camera into electronic image that we later on pass through the system as a video signal. The photo effect was discovered by Heinrich Hertz back in the 19th century and successfully explained its principles by Albert Einstein in 1905. And in fact, Albert Einstein won a Nobel Prize exactly for this explanation of the photo effect, which is, as I said, very important for us in closed-circuit television. We have 5 senses with which we experience the world around us. That's how we learn. Eyes are one of those 5 senses. And it happens that eyes participate in our learning about the world around us the most. In fact, statistically, it has been proven that visual perception contributes over 75% in our learning for the world around us. The hearing contributes with only 13%. Touch contributes with about 6%, smell with about 3%, taste with about 3%. So visual perception is the most informative. It actually brings information to our brains for the world around us more than any of the other 4 senses put together. So it's no wonder somebody said the picture is worth 1,000 words. And of course, for us in closed-circuit television, the actual visual perception is what we would like to see through the camera. So in a way, the closed-circuit television cameras, we try to see the world around us through the eyes of the lens to be similar or equivalent to our perception with our eyes. So we need to understand how we see. Back in the 19th century, English scientist James Clerk Maxwell asserted that the light is an electromagnetic radiation. In fact, this model, this theory has been accepted as correct. And even today, we understand light as electromagnetic radiation, no different than other electromagnetic radiations we have around us, such as radio waves, microwaves, X-rays or gamma rays. It's just only a small portion of the whole spectrum of electromagnetic radiation. In fact, there is no difference in principles what light is compared to the, let's say, radio waves that you use with your mobile phone to pick up signal and communicate with the world around us. It's actually just a part of that electromagnetic radiation spectrum that we don't see. The radio wavelengths, the radio waves we don't see because they are way out of the visible range of the electromagnetic spectrum. The part of the electromagnetic spectrum that we pick up with our sensors, with our eyes, ranges from about 700 nanometers to 400 nanometers. This is the wavelength range, and that can be converted in frequency, which we'll show later on through some of the examples we have. But it is important to understand that all these different wavelengths, from 700 nanometers as a longer one to the 400 nanometers as shorter ones, we see as colors. So, for example, red would be around 700 nanometers. Yellow will be a little bit shorter than that, perhaps about 600 nanometers. Green is 555 nanometers, the peak of. And then we've got through blue to violet, which is about 400 nanometers. So in our eyes, we have sensors which are actually sensitive to different wavelengths in a different way. This sensitivity is called human eye spectral sensitivity. That ranges from 700 nanometers to 400, and it peaks at about 555 nanometers, which is the green color area. It is a bell-shaped curve, but it is typical for human eye, although there are people that are, for example, by birth colorblind. That means that some people cannot distinguish colors as much as the rest of the population. But we will talk about an average human eye, and this is the spectral sensitivity of an average human eye. Now, the interesting part to understand for CCTV is that there are wavelengths that are longer than 700 nanometers, which go into the infrared region spectrum, as well as there are wavelengths that are shorter than 400 nanometers, which go in the ultraviolet range of the spectrum. We don't see them, however, there are some species, for example, that can see infrared. As we all know, species such as snakes or rats or cats, they would actually see in the infrared region simply because with the evolution, they actually have evolved and extended their vision abilities because their survival was at stake, and evolution obviously chooses the best way to sustain particular species. So if we don't see infrared, it doesn't mean that nothing else or nobody else sees it. We only see from 700 to 400 nanometers. These are approximate wavelengths. Certainly there is no clean cut. Some people may have a little bit more extended range, some of them a little bit narrower, and similarly to the other side of the spectrum, like the violet. But in any case, this is an average spectral sensitivity of human eye. Now, there is a link, there is a connection between the actual frequency of the particular colors, which are proportional or to the speed of light, and inverse proportional to the wavelength lambda. So, for example, if we have a frequency of 555 nanometers, which corresponds to the green color, the frequency of that wavelength can be found as speed of light 300 times 10 to the power of 6 meters per second, divided by 555 times 10 to the minus 9, and expressed in meters, so from nanometers to meters. That gives us about 540 times 10 to the power of 12 hertz, which is actually terahertz. So the green color of 555 nanometers is actually a wavelength, and the frequency of it is 540 terahertz. An interesting observation can be made of why human eye has a peak at green color, 555 nanometers, and why does it look like what it looks like. This is an interesting question that I have been puzzled by, and during the research for writing my books, during the studies, I've found the material where it says that from all the sun radiation that comes through the Earth's surface, so penetrates through the atmosphere, actually the green color is contributes with the most energy. So out of all the wavelengths, certainly infrared comes down. We feel it as a heat from the sun, but the amount of energy in the green is the strongest, which is why the evolution on the planet has evolved to pick up those energies from the green, mostly green wavelengths, and hence we have the green grass, green trees, and in fact opticians, people that obviously would analyze and will tell you what is good for your eyesight. They will tell you that you need to rest your eyes by looking at something green, by relaxing and looking in something green like trees and grass and in the nature, simply because the energy that comes from that wavelength excites the eyes easiest, so you don't have to put an effort, let's say, to see, and you feel like you're relaxing by just simply looking at the green color. A very simple but interesting observation. Now, in CCTV, we use a slightly different spectrum because that depends on the camera spectral sensitivity. This is the imaging sensor, which could be the CCD chip in the past, charge coupled device sensors chips, or these days the most popular CMOS. Either way, both of these solid state sensors have certain spectral sensitivity curve, and in fact that spectral sensitivity curve is more extended into the infrared region spectrum. So here in this drawing we have the dotted line that picks in the middle of the drawing, which is about 700 to 800 nanometers, is an average spectral sensitivity of an imaging chip, which is also expressed and explained by the quantum efficiency, so-called. What that means is that if we consider our human eye spectral sensitivity at the bottom left-hand corner, which is illustrated here with like a rainbow colors, we will see that the spectral sensitivity of the imaging sensor does not match the spectral sensitivity of human eye. This is a very important observation so that we can understand why we need to have infrared cut filters. And infrared cut filters are put in all color cameras, the one that we want to produce color, because in order for the imaging sensor to produce a picture that will look similar to what we observe with our eyes, we need to modify this spectral sensitivity of the camera and try to model it to match the spectral sensitivity, or the bell-shaped curves, if you want, of the human eye. That way, that is the only way we can recognize colors the way we see it. So the camera, we make the cameras to see colors to be similar to human eye. That is a very important observation that actually can explain why is it that we have this green piece of glass on top of the sensor. The idea is that you need to remove the infrared portion of the radiation that the camera naturally sees. Now, this is all good and well for seeing color pictures. What happens when we want to see infrared illumination, like at night in surveillance, in closed-circuit television? We very often use infrared illuminators to see at night, simply because there are no other sources of light in most of the surveyed areas. And infrared lights are also inconspicuous, so that human eye does not necessarily see them, because they could be in the 855 or 850 nanometers range, for example, some of the typical infrared radiation. But in any case, human eye does not see them as sensor would see them when the infrared cut filter is removed. So the infrared cut filter is in fact optical low pass filter. Without the infrared cut filter, we cannot see colors, but if we want to see black and white with the infrared illumination, because it's basically a frequency that is out of this visible range, we need to remove the infrared cut filter. And this is happening in most of the cameras by way of mechanical removal of this filter when it gets dark. When the signal is reasonably low in intensity, so the illumination is very low, then the camera instructs the infrared filter to remove, and suddenly we lose the ability of seeing color with the camera, but we see the infrared illuminator as almost normal floodlight, and we can see what is happening at night. And let's now go back to the human eye and see how it works. So the cross-section shows that the eye has a lens that focuses the image onto the retina. The retina is a photosensitive area which is located on the back of the eyeball on the inside. So it's on the right-hand side of this cross-section. The retina is a photosensitive area which is composed of millions of cells called cones and rods. These cells can be considered as part of our nervous system because they are sensitive to the light, but in different ways. The cones are the ones that are sensitive to the medium and bright intensity of light and colors. We see colors through the cones. The rods are cells sensitive to lower light levels, like night vision, and they do not distinguish colors. So we use rod cells to see at night, which means when it is dark, we cannot distinguish colors. Now, there are some more interesting facts there, but let's say just a simple statistics and numbers so we understand how well we see in terms of resolution. There are about 10 millions of cones in our eye, and the number of rods is about over 100 million. The cones are concentrated around the area where the optical axis is, and that is this horizontal dotted line called optical axis or direction of vision. The main interest, the interest of what we see is usually in this area. So at the back of the eyeball, there is a colored area with yellowish pigment which is called fovea. So this is where the high resolution imagery happens. This is where we see details. The fovea is the central area that our brain processes, and although it is a small area, the concentration of cones there is approximately about 50,000. So the average focal length of an eye is approximately 17 millimeters. So this is the length from the eye that projects an image onto the retina. Now, maybe we should also see it from the perspective of a camera. The eyes are projected, the lens projects an image to the retina upside down, which is the optical way of how images are being projected. So whether it's a real piece of glass, magnifying glass, or human eye, the image both on the camera sensor and on the retina are projected upside down. It is the brain that converts that image to normal, so we don't even know it's upside down, but the processing happens as if that is not upside down. The actual diameter of the eye lens is about 6 millimeters, which is also an interesting observation, because from that you can kind of find the f-stop, or the light gathering ability of the human eye. And when it's very dark, with the darkest area, when the iris is fully open, the f-stop is equivalent to, that's defined in optics as focal length, which in our case is 17 millimeters, versus 6 millimeters as the widest opening. That is equivalent to about 2.8. So f-stop of human eye is 2.8, equivalent to 2.8. Now, the focal length gives an undistorted image in a solid angle of approximately 30 degrees. This is also the size of the area most populated with the cone cells. This is why an angle of about 30 degrees is considered a standard angle of vision. This is interesting for people doing photography, for example. If you remember in the past when we had films, we had a standard lens of 50mm for the Leica format for a film camera, and 50mm was actually giving you the perspective of the picture that a camera would take of a similar proportions as human eye would see. That's why it was called standard vision. So you can say, or we can say, that all angles of view that are wider than 30 degrees are called wide angle lenses, and similarly all angles of view that are narrower than 30 degrees are called telephoto lenses, which we will see later on in the optics section. Another interesting thing is to highlight that the iris is the one that is controlled by the brain without our knowledge. So it's like involuntary, So it's an involuntary control by the brain, where if it is too much light, the iris closes. So it's like f-stop closing down. If it is dark, we come out from the outside into the internal of a building, then iris fully opens up to gather as much light as possible. Very similar principle that we have in normal photographic camera or CCTV camera. Now, this is an involuntary control by the brain, or unconscious if you want, where you cannot force the iris to open or close. And it's an important function of the brain because it protects the eye, it protects what we're seeing. It does automatic regulation of the light incoming into the retina, so we don't burn the retina and we don't damage it. And it is also an indicator of human brain activity. It is known that many doctors, specialists, when they have an emergency call and a person has been hit in the head or fallen unconscious and he's lost his conscious, the first thing they usually would check is open their eyelids and shine a torch with light into the eyes. And if the iris closes down to protect the retina, that means the brain most likely is still okay. But if the brain doesn't close the iris, then chances are there is a damage to the brain, or maybe permanent damage or fatal damage. But in any case, it's an important function that we need to understand is automatic, and it is similar to what we will see later on in the CCTV. We have automatic iris control of the lenses. Now, another interesting thing to mention here is that every of these retina cells has direct connection to the brain with optical nerves, where the signal is actually taken with electrochemical pulses. So in a way, we've got a little circuitry that actually works like in a camera. We send pulses, in fact, of what we see. So kind of information is really digital because it is with the intensity that fires neurons, and the neurons are firing only above certain level when they're excited. And kind of digital communication, it's already happening in our heads all the time in the evolution, even though in CCTV we only switched to digital in the last 10 years. Now, an interesting trivia or interesting thing to know also is the correcting of the eye vision. It's a interesting and very common thing to know. For example, it all depends on whether the lens focuses the image on the retina precisely. That means whether the lens works the way it's supposed to work. Again, this is an involuntary control by the brain. So we actually just point the eye to an object we want to see, and then the thickening and thinning of the eye lens is achieving focusing. If we see objects in the distance, then the eye lens thins, becomes thinner. As the object comes close to us, like in the top two drawings, you will see top two models. Further object is thinner lens than the object or person coming closer. Lens thickens to project the sharp image on the retina at the same time when the object comes closer. Now, if a person has got a problem, deficiency with the eye. For example, he cannot see clearly an object that is far away. Usually that means the lens is very thick, bubbly, and the so-called ancillary muscles, which are controlling the lens by contracting and extending it, cannot flatten it, cannot make it thin enough, simply because they've been, for any reason, in that position. It could be a person reads or watches television from close distance often, very often, and suddenly the eye gets used to that and doesn't have enough strength, let's say, to thins the lens. In which case, you would require to wear negative glasses, negative diopter glasses, to fix such a bubbly lens of your eyes, to make it thinner by combining negative and bubbly lens that you have in your eyes. Equally, the lens of the eye can be very thin, and it doesn't get any bubblier simply because it may be aging process, which is very common when people get older. They all need to wear reading glasses, as they call them. Reading glasses is simply a magnifying or positive diopter lens, which compensates for the inability of the human eye to focus on something closer. So these are the simple explanations about the eye as an optical element, and we see that those concepts are very familiar, since most of us would be aware of wearing glasses, and it is applicable to CCTV as well, as we will see later on. Let's now jump to a simple comparison between the eye and the camera, so we can see the similarities between these two instruments, if you want. And there are many of them, even though some of them are completely different. Both camera has got a lens, like eye. The camera has a sensor, like we have retina. The camera has got electronic processing, like our brain, you can say. We have irises that opens and closes depending upon the amount of light. Most cameras have auto iris, which does the same thing. Now, the difference is in human eye, the focusing is achieved by thickening and thinning of the lens. So it's only one optical element that ancillary muscles thicken and thin based on where we want to focus. And assuming we've got healthy eyes, then we can see clearly from very close distance to infinity. The cameras achieve the focusing slightly different. They don't have lenses that can thicken and thin, but rather they are optical elements, crude pieces of glass that are put together in such a way, and the focusing is achieved by moving certain optical elements forward or back. In fact, that is usually achieved by the front group of elements called objective, and the focusing to a closer distance moves the objective further from the sensor, away from the sensor. As the object we are looking at is further away, the objective, or the groups of lenses that achieve the focusing into the further distance, comes closer towards the sensor. So focusing is made by moving groups of glasses, which is what we do with the actual photographic camera. We actually focusing, if it is manual focus, of course, we are focusing by turning a ring, which moves groups of glass of lenses back and forth. The point is to understand that this is the conceptual difference to the human eye, and we need more pieces of glass to have certain optical corrections, as we will see later on. But just an interesting digression here. Already there are designs of so-called liquid lenses, which are actually achieving the focusing similar way like human eye, by thickening and thinning certain transparent liquid by way of electrostatic voltage. But again, we have not spent time researching this for the book, simply because that's only new. But sooner or later, I believe that they will become very common in any visual industry, including CCTV, and hopefully we will be witnessing this very soon. As we are discussing the human eye vision in this lecture, we really should also say a couple of words about the human eye resolving power, or the minimum details that we can see with our eyes, or the maximum resolution we can see. There is a limit to it. And it's interesting to know that with experiments and testing, it has been found that the most the human eye can resolve is no more than 5 to 6 line pairs per millimeter, which is viewed at a distance of about 30 to 50 centimeters, something which is similar to reading a book, very nicely and finely illustrated book perhaps, or reading a smart pad with very high retina display, as they call them lately. And this actually is equivalent, that sharpness of 5 to 6 line pairs per millimeter is equal to about 1/60th of a degree in terms of angle. So this is considered, the 1/60th of a degree is considered the limit of angular discrimination for normal vision. As you can see in this illustration, this is shown as an eye looking at very fine number of lines next to each other. So if these lines are smaller than 0.1 of a millimeter, it will be very difficult to see, even with the best healthy eye. In my teachings and seminars, I use an example of how I can best describe what is this minimum thing that you can see. Typically, if you have a mechanical watch made in Japan, made in Switzerland, usually they have at the very bottom of the face made in Japan, or made in Switzerland, or made in Swiss. Now, these are so fine letters that are engraved with usually about 0.1 of a millimeter thickness. It is, even for a healthy eye, very difficult to read them. You often need to have magnifying glass to see it. So that's kind of limit of what we can see. And it is defined by the actual size of the cones and the cells on the retina. Remember previously we said how many of them are around 50,000 in the very dense area where we see details. So this size of the cones and cells and the number of it in the retina area, in the fovea area, define this minimum angle of vision, or the maximum resolution. There is a simple way of finding out, based on this, what is the optimum viewing distance for us when we are watching, let's say, a television, large screen, or any kind of display. This is very useful to know for designing control rooms. In my designs, in my consultancy, I've used this very often to the satisfaction of the customers, and obviously pleasing to the operators, and delivers really the best picture using exactly the same high definition or ultra high definition images. So if you imagine that you have a high definition screen at a certain distance, think of this 5 to 6 line pairs per millimeter size as a projection on the pixels. So the distance at which this high definition screen is such that you can no longer discern the pixels, this is the distance that is most informative for human eye. If the monitor is further away to that distance, I would call it optimum viewing distance, then you no longer see the maximum resolution that a picture can give you. If, however, that monitor is much closer than this distance, then you start seeing, recognizing the pattern of the pixels of the screen, which is basically bigger than the minimum resolution of 0.1 of a millimeter we have with this previously stated finding. So in simple terms, depending on the size of the display, and of course on the resolution, which defines the pixel size of the display, typically in monitors this is called the pitch. The pitch has to be equal size at such a distance as if you project the 0.1 of a millimeter, which is about 30 to 50 centimeters in front of you, when you have, if you have the 20/20 vision, if you're eyes are very healthy. So using such a logic and thinking, we actually can say there is always some optimum viewing distance for different size of monitor and different resolution. So typically reading a book or very fine retina display, iPad if you wish, 0.3 to 0.5 of a meter is the optimum. And if you go further away with the iPad, you are losing a little bit simply because the pixels are getting too small for you to recognize. If you come closer than that optimum viewing distance, you will start recognizing the pattern of the pixels. And in fact, the optimum vision is where you just about not recognizing the pixels. So the minimum resolution or maximum resolution or minimum angular discrimination for the normal vision is equal to the pixel size of the display. In this image, we have a representation of the old style of monitors, analog, but also some high definition monitors of different sizes. And as you can see, there are some rules where, for example, a 55-inch high-definition screen with 1920 by 1080 pixels, the pixel size is such that the optimum viewing distance would be about 1.9 meters. So basically, using the same logic, you can find optimal viewing distance for any monitor size and any resolution. All you have to know is the dimensions of the display, the active dimensions of the display, so not the one that are extending with plastic, but actually the display. So if you find out the dot pitch, which is the smallest pixel element on that display, then you can easily do a proportion and find out what is the optimum viewing distance. For example, if we have a 55-inch LCD display, for example, 55-inch you can find out on any website. Most of them would quote active display dimensions of about 1210 millimeters by 680. So if you divide 680 millimeters, which is the height of the HD monitor, 680 divided by 1080 for the number of lines we have on a high definition format, the dot pitch or the smallest pixel size or the pixel size in such a display would be 0.63 of a millimeter. So using the proportion, as you can see on this drawing, you will find out that the optimum viewing distance for that monitor will be about 1.9 meters roughly. The variation in the minimum distance from the for the 0.1 of a millimeter resolution on this drawing, it says 0.3 to 0.5 of a meter. That means different eyes, different people may see better at about 30 centimeters, which for some may be just too close, up to 40 to 50 centimeters. But in any case, the maximum resolving power of the eye is statistically found based on testing of people that they can read small fine print from the comfortable distance, which is typically for a healthy eye 30 to 50 centimeters. So this is why the minimum of viewing, optimal viewing distance, if we assume this is 30 centimeters, would be in this case for high definition 55-inch screen about 1.9 meters. Similarly, you can find dimensions for any size monitor, whether it's HD or UHD. All you have to find out is what is the dot pitch size for that monitor, and that will give you an idea what is the optimal viewing distance. Now, this is not a rule set in concrete, so it doesn't mean you can't put the monitor at 1 meter rather than 1.9 or at even 4 meters rather than 1.9. It just says that the psychophysiology of human eye and the brain works the best. You really see optimum details in the picture simply because you do not get confused with the raster, with the actual pattern of the pixels if the monitor was closer. And similarly, if the monitor is further away, you are not losing the frequencies that the pixels can show you. So this is the trick that depends on the human eye resolution, which is defining the optimal viewing distances, ideal knowledge to have and apply when designing, let's say, monitoring control rooms, and have the best experience for the operators. Talking about light and human eye in this lecture will not be complete without saying a few words about the eye deficiency called persistence. In fact, this is a deficiency of the human eye that we use to have an illusion, to get an illusion of motion pictures. Human eye has this ability of persistence, which actually is symbolized in remembering of the image that we see at this moment a few milliseconds after the image disappears. All of us would remember the time when somebody with a camera and a flashlight takes a picture and flashes the light in our direction. If we're not prepared for it, we didn't know, and we did not close our eyelids, the flash itself, the impression of the strong light of the flash, will stay in our retina for quite a few milliseconds. That is the persistence of human eye. And we use that actually to create the illusion of motion pictures, of moving pictures. All motion pictures that we know of, which is cinematography, television, and closed-circuit television, are nothing but static images that are projected at a very fast rate, that we see them as moving pictures. So in other words, we cannot see they are individually static, but we have impression of moving or motion pictures. This is simply because of the persistence of human eye. Similarly, people that have been preparing or making flip books as children, we all know flip books where you draw on the number of pieces of paper images which are logically consecutive, perhaps a moving person, and every single drawing, every next drawing is logical sequence of the movement. When you flip that book very quickly, you actually have illusion of moving. Exactly that deficiency of human eye, called persistence, is used in cinematography. One of the very first movies that was made in 1895 was the Brother Lumiere's The Train Arrival. This is a motion picture that actually was created with 24 static images a second, and once it was shown and projected, it created the new industry, the motion picture industry. When the cinema picked up, being very interesting and new medium of entertainment at a very early 20th century, the cinematography started becoming so successful that people started building cinemas, bigger and better, with stronger projectors, which actually caused the flicker of motion images. If the same 24 pictures a second recorded by the film camera was projected in a much bigger cinema with much stronger, more powerful projectors, it was noticed that people start seeing a flicker. And that flicker became annoying because the frequency of 24 pictures a second, the initial frequency that the cameras were exposing the film 24 times a second to produce motion picture, were not sufficient if the projection was too strong. So ingenuity of motion pictures engineers found out that actually you can still have 24 pictures a second, but we can interrupt the projection of every of these frame, every of these images, by so-called Maltesian cross. And Maltese cross is a little mechanical device that is actually rotating in front of the projector lens and is divided like a cross with two areas that are transparent and two areas that are blocked, as shown in this picture. And basically that rotates with the revolution of 24 revolutions per second, which means it will produce 48 projections in the same second of that film. So in other words, the one frame that was shot at a duration of 1/24 of a second suddenly was divided in two by interrupting the projection and then projecting it again, so that 24 pictures a second became 48, even though out of those 48, really only 24 were different. But very clever way of increasing the projection speed from 24 frames per second to 48, and it was actually avoid the flickering of the screen became flickerless, so people were not annoyed with it, and suddenly we had 24 pictures a second recording by the movie as motion pictures projected at 48 times a second, which gave the illusion of smooth continuous motion pictures, even though each one of these 24 exposed images was still image. So it's interesting to know that the same concept we use in television, where depending upon the continent and the country, where the mains frequency was 50 hertz, for example, in Europe, and 60 in US and Japan, we actually had television projecting 25 frames a second, which were divided in so-called television fields, which were 50 a second for PAL, and 30 frames a second, which were divided into which we'll explain later on how, but they were divided in two, so 30 images were basically projected as 60 television fields a second. That gave illusion of motion pictures. So, in other words, both cinema and television, like CCTV, we do nothing but we are recording and projecting still images, but at such a fast rate that our eye, because of the deficiency we have called persistence, sees them as motion pictures. This dependency can be described like with this curve shown here. The dark blue area is the area of noticeable flicker. On the horizontal, we've got screen brightness. That could be a television screen, could be a cinema screen, but certainly goes higher as we're going to the right. And on the vertical axis, we've got pictures per second. So the yellow area is area of motion pictures flickerless area. So this is basically saying that if we choose, let's say, 30 frames a second pictures, 30 pictures per second at, let's say, 0.1 or 1 of this scene brightness, which usually would be measured in nits as a unit of brightness of the screen, will be without a noticeable flicker. If, however, the same 30 images per second we project with very bright, much brighter, or show it on a much brighter screen of, let's say, 100 nits, then that may become very annoying, which is basically removed by increasing the frequency of that. This is the graph that shows you that early films were done with 24 hertz or 24 films per second. As you can see, the actual screen brightness was somewhere around 10 units over there, as shown on this graph. Then when the cinema started becoming more popular, brighter and stronger projectors were used. That needed to be increased to about over 40, in this case 48, as I said, with the Maltese cross, in order not to see the flicker. And finally, we are coming to the pictures per second of frequency of refresh rate of still images in television has to be over 47 hertz, as we know. 50 hertz or 50 television fields we've got in the old PAL system, and 60 in the old NTSC system, which now converted to digital is 30 frames per second or 60 frames per second. Now, the size of the screen, the brightness, the new technology that we are bringing up indicates that we have to have higher frame rate, even even higher than 25 or 30 frames a second. So this is why, even though the television camera or even CCTV camera may be recording at 25 frames a second or 30 frames a second, the display, if it is huge, bright display, may have 60 frames or 120 frames refresh rate a second. Now, this refresh rate is not necessarily 120 images a second, but is refreshing the same image recorded at 30 frames per second up to 120 times a second, in order for us not to see flicker, because this diagram indicates that the bigger, the brighter the screen is, And in actual fact, the closer the screen is to us, it's also a factor, which is a little bit beyond this lecture, but closeness also influences the peripheral vision, which is sometimes more noticing the flicker. So the brightness, the size of the screen indicates or defines how many images per second we should have in order for our eyes not to see flicker, which is a result of the eye persistence function. So this was an important part of the eye characteristics. This was important characteristics of the eye to understand, because this is the basis for all motion pictures, from cinematography to television to closed-circuit television. I hope that explains everything you wanted to know.